Okay, welcome back everybody. Today we're going to solve our first PDE, and it's probably the most important PDE if you ask me. We use the heat equation all the time for all sorts of reasons. It's kind of the most classic PDE that you can solve. And the way we're going to do that, we'll see the way we do that later, but let's just talk about what the heat equation actually is first, maybe why it exists. So we've got this bar at the bottom of the screen where we have x1, x2, x3, blah, 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 all the way up to xn. Okay, so we're just going to say this is a bar considering n nodes. I'm going to call each one of these a nodes. And every node has this constant between itself and its neighbors. So k1, k2, k3, and so on. Okay, so we have constants from that talk about nodes interacting with their neighbors. What do we actually want to do with this bar? Because it's just a bar that I've decided to call a bunch of different pieces, x1 through xn. What I want to do is I want to assign a temperature to each xj. By each xj, I mean each node. Okay, so each node is going to gain a temperature, and I need to ask the question, then ask, how does the temp change over time of each bar? Now, to know how these change over time, what I've done is given these k's. The k's are heat conductivity relations. Okay, so in some sense, you can think about each of the x's as maybe buckets of water, and then each k is a metal rod connecting the buckets of water. And each of the metal rods have some different alloy or composition to them, so they can conduct heat in a different way. This is heat conductivity between each node. And when we think about it, if I have a total amount of temperature in my buckets of water, then as time proceeds to infinity, as long as each k is non-zero and I can conduct some heat, eventually I'll end up at equilibrium. But we care about like the change at some finite time that's not equilibrium. So suppose I did set this experiment up and waited like 10 seconds, how would the heat have changed in 10 seconds or something like that? So how do we actually set this up? Well, it's not a PDE yet. It is, in fact, 14.2.1, which we saw earlier in this chapter. We called it a heat system, right? So this is the heat system where I only have x1, x2, and x3, or I've relabeled x's as u's here. But what we can see from these heat systems is that the change in heat of u1, it loses heat depending on how hot it is. So the hotter u1 is, it's going to lose that much heat because the rate at which it loses heat is faster. You can imagine the hotter an object is, the faster it's going to radiate heat out into its environment, but it's also going to gain heat from its neighbor, and its neighbor in this case is u2. So k1 describes how fast it loses heat, it describes how fast it gains heat, and it can only possibly gain heat from u2. That's what we think about. And then how does u2 depend? Well, it loses heat perhaps over to u1 through k1, it loses heat over to u3 via k2, and it can possibly gain heat from both u1 and u3. And that's where the signs are changing, right? The negatives are it's losing heat, the positives are it's gaining heat, and so on with u3. So there's nothing particularly special about that. It's a very natural system of equations to produce, and we already saw it quite a few days ago. But I'm going to jump back down to where we are here. When I have a big system of these, what I want to do, and then this is why if I jump back to the name of the chapter, in chapter 14 it said modeling in the quote-unquote continuum limit. The idea with the continuum limit is that if, I'm going to write this down here, if I let n go to infinity at the same time as letting the distance between the x's tend to 0. So I'm going to bring my nodes closer together, but I'm going to make an infinite number of nodes. And then I recover a continuous function with a continuous idea of metal rods, infinitely small metal rods, giving infinitely small points a different conductivity. And I ask the question, how does the heat change throughout that system, which is much more common to what we think about in real life, where every infinitely small object, I guess not infinitely small, but maybe atomically sized object, has some sort of energy. How does it transmit its energy to its neighbors? And it does so technically through electronic interactions, but it's going to, we can model the electronic interactions with some conductivities. And if we take that limit correctly, we recover the following right here. I'm going to highlight it right here. So what we have there is a difference quotient. And the difference quotient is not the standard one we're used to when it comes to derivatives. But if we put a little bit of work in to actually figure out what this difference quotient represents, we would find out it's not quite the derivative. It's not quite the second derivative. It's this interesting interaction between a derivative ddx, a second derivative ddx, and in fact the conductivity, however we've defined our conductivity, in between those ddx's. So it's some sort of pseudo second derivative, but with this special conductivity in between the two of them. And that's what we recover in what's called the continuum limit. And that's how we can actually derive this heat equation, if we want to, for any sort of material which has maybe a non-trivial conductivity. If the material is perfectly uniform, then the conductivity doesn't depend on space, and so that actually just becomes a constant. It becomes what's called the conductance, heat conductance of the material. But if the material is not uniform, then the conductance of the material changes over space, and we have to factor that into the heat equation, and that's how we would do it. So this is the heat equation. Forget about the F right now, right? The F would be there if we had some original extra forcing in our original system. Like I said the other day, it's if we have a candle in the room or something like that. The candle is going to interact with the heat at any point in space. But, that's just me deriving it for you. Today, we're basically going to be looking at this and saying, okay, can I actually solve this PDE? And we can do that. I'm going to skip through those parts. Those aren't terribly important. Right here, solving the heat equation. So we're going to solve the heat equation right now. And we're going to solve it in a one-dimensional setting and also what's called a source-free setting. So this is no candles. Right. So we're not going to put a candle in the room. And we're also going to simplify it so that heat conductance equals 1, constant everywhere. So when I solve it, no candles, that would be f of x equals 0. Heat conductance equals 1, and it's constant everywhere. If I jump up to here, that's me saying I'm letting k be equal to 1, I'm letting f be equal to 0. And so what I recover is partial t is partial x squared. So jumping back down, there you go, partial t, I've moved to the partial x squared to the left-hand side and recovered a negative sign in response. And let's talk about solving this. So this is kind of the classic PDE that a lot of your instructors are going to ask you in the future, do you know how to solve the heat equation? And this is the one they're referring to. They're not referring to the non-trivial one that we experienced earlier, where the conductance is non-trivial. There's a source, so there's a candle in the room or something. That's a completely different situation. Your instructor cares if you can solve this equation. And you're going to tell them yes, because what you do to solve this equation is start by assuming that the solution is a multiplication, boy I can spell, multiplication of a spatial function and a temporal function. That's my multiplication, f, g. So I'm multiplying a spatial function by a temporal function, and I'm assuming this is how you can find a solution. You might be wondering why this is a valid assumption to make. It is not. The only reason we're allowed to do this is because somebody 100 years ago, actually it was like 350 years ago, maybe 250 years ago did this for us, and they solved it in much more trickier ways, and then they figured out that it's a multiplication. But taking a step back and just saying, yes, it's a multiplication of the two of them, then this, by the way, this process of having a multiplication of these two separate functions is called separation of variables, because the variables x and t have been separated into separate functions. We just make that assumption, and then we evaluate the derivatives on this function. So forgetting about what's happening below, let's actually go through this in our head so we make sure we're doing everything correctly. Let's evaluate the differential equation on u. So to evaluate partial u, partial t, if u is equal to f of x, g of t, then the only thing that my derivative in t sees is g, right? F of x is sitting there along for the ride. And so I recover f of x, g prime of t. I can then go about evaluating partial squared u, partial x squared. And if I assume that u is this lovely product of f of x and g of t, then the partials in x only care about f. They don't care about g because g is a function of t. And so what I recover out of that is two derivatives in x, and I'm left with the g of t. Okay, so the heat equation then says that one derivative in time on g is equal to two derivatives in space on x. So I'm going to jump over to the whiteboard, take a quick moment to memorize what's sitting in the purple highlighter here. F of x g prime of t equals f double prime x g of t. Over to the whiteboard. Like I said, if we memorize correctly, it was f of x g prime of t equals f double prime of x g of t. So you can reverse the video if you want to make sure that's what it said. But this is an equivalent to heat equation, assuming, right, this is that special assumption, assuming u equals f of x g of t. So that's equivalent to the heat equation. I then get clever. There's something very clever that we need to do. And that's that we divide both sides by f of x g of t. The reason why is because what I'm trying to do is isolate functions of x on one side and functions of t on the other. It's useful because the g of t's cancel there, the f of x is canceled there, and I'm left with g prime t over g of t, t, make sure I use the right variables, is f double prime x over f of x. Time to get clever one more time, and I'm not entirely sure a lot of you will follow me on this because I didn't follow myself the first time I studied this. This was like 10 years ago, but still, first time I studied this, I had no idea why we were able to make this next claim. But let's think about it this way. Suppose this is not constant. So suppose I have some function of t, only the left-hand side, we're looking at just the left-hand side. Suppose that the left-hand side is not constant, as in it evolves over time. So the left-hand side evolves over time. I want to say this really quick. Hence, left-hand side, LHS, evolves over time. Well, something important to say is that the right-hand side equals the left-hand side. Well, if I have something that evolves over time on the left, and the thing on the right is equal to that, then the right-hand side evolves over time. Right? So if the left-hand side evolves over time, and the right-hand side is equal to it, it must also evolve over time, but there's no time variable here. There you go. So there's no time variable on the right-hand side, so that can't be true. The right-hand side cannot evolve over time. Therefore, the left-hand side can't evolve over time either. And in fact, that means that the left-hand side has to be equal to a constant. We use the Greek letter lambda oftentimes in these sorts of arguments, but you can use whatever constant you want. I'm going to stick with lambda. So hence, the left-hand side is a constant. So since the right-hand side has no time variable, the left-hand side is a constant. We can make the same argument, right? Especially now that we know that everything is constant. The left-hand side equals the right-hand side, but the left-hand side equals constant, therefore the right-hand side is also equal to a constant. So we get really lucky here, and we can say that both sides individually equal a constant. They individually equal the same constant. And this is a little bit tricky to get used to as well. Therefore, we have not one, but two ODEs. You're going to be curious where my two ODEs are, but one of them is right there. F double prime x over f of x is a constant. And the second one is right here. G prime t over g of t is a constant. And they happen to be equal to the same constant, but I have two ODEs. So I'm going to erase everything else on the board except for those two ODEs that I just came up with. And if this is a little bit confusing for all of you, we will be spending 2 days on this to get a little bit more. I'm just deriving the heat equation for you for now so that you can get used to it and then come chapter 15, we'll study this a little bit more intently. So you don't have to let everything work out in your mind right away, but it's good to get used to. So we actually have 2 ODEs instead of 1 PDE. Hence, 2 ODEs instead of 1 PDE. If I rewrite the first ODE by multiplying both sides by f of x, I have f double prime x is lambda f of x. You all should be able to solve this. This happens to be solved with, I guess it's cosine. Let's see. Oh, it's yeah. We'll say I'm gonna put a negative sign in front of my lambdas here and here. You'll see why in a bit. So I'm gonna put negative signs in front of there. It makes my life easier. You'll see why in a bit. Lambda, we don't know what the constant is yet. We just know that it is a constant. I'm gonna put a negative sign there. And because of that, I'm gonna say this is solved with f of x is cosine lambda x plus sine lambda x. And if you recall from your section on ODEs back last semester, these have constants in front of them. And these are square root of lambda. Okay, so you can go through your whole process of ODEs last semester to get that. I'm going to assume you already know how to do it. And we're going to do the same thing with the g's. If I multiply both sides there, I have g prime is negative lambda g. And from ODEs last semester, we know this is solved with g of t is the exponential negative lambda t. C3 e to the negative lambda t. So you should remember that from last semester. This was your chapter on ODEs stuff. Don't worry why I swapped lambda for negative lambda. It doesn't actually matter. Either one would have given us perfectly fine results, but it makes our lives a little bit easier to make that assumption. Okay, so let's jump back to recall that u of x and t was equal to f of x times g of t. So we're just going to grab f of x, and we're going to grab g of t, and we're going to multiply them together. So when we multiply them, we don't know what our constants are still, so I'm just going to call it c1 e to the negative lambda t cosine root lambda t plus c2 e to the negative lambda t sine root lambda t. That's the solution to the heat equation. This is true for any lambda greater than or equal to 0. Because when lambda is less than or equal to 0, the square roots don't really make sense. And so we actually have a solution for any lambda greater than or equal to 0. Why is it that heat only behaves in one way? Well, that's what initial and boundary conditions are for, right? So we have our solution here, but once we actually evaluate some sort of system, we also include initial and boundary conditions. So we're going to jump back to the book and consider initial and boundary conditions. Okay, so jumping back to the book, let's scroll down a little bit. You can see they recovered the same solution that we did. They used A and B instead of C1 and C2. But we're going to consider some initial and boundary conditions. So let's take our domain to be in space. That's omega will always refer to the spatial domain. So the spatial domain is 0, 1. There you can see our boundary then becomes x equals 1 and x equals 0. And we're going to say that these are Dirichlet boundary conditions and fix both of them to be equal to 0. The initial conditions occur at time t equals 0, and they evolve over space. And let's just make the assumption that the initial condition is equal to sine. So now suppose I have a system. Here's what I want to think about, is that I start with the sine curve between 0 and 1 of sine pi t. It looks like this, or sine pi x, between x equals 0 and x equals 1. And I want to fix the boundaries at 0. So I'm going to say the heat on the boundaries is 0. How does this behave over time as time evolves forward? How does the heat change? What we'll see is that the heat decreases over time. So as t gets larger and larger, the heat should decrease, which makes sense because the boundary is basically like me saying I'm putting blocks of ice at 0 and 1. That's the only way to get the temperature equal to 0. 0 Celsius or something like that, right? Okay, so there is our solution we had before, and now we actually have to solve the initial and boundary conditions for this solution. If I scroll down a little bit, let's start with the boundary conditions. And I know that the value of u at 0 in x needs to be 0. So I'm going to plug 0 in for x and see what I end up with. Well, sine of 0 is 0, so that piece is gone. Cosine of 0 is 1. So what I recover is b e to the negative lambda t equals 0. And the only way for that to be true for all times, this needs to be true, satisfied for all times, is when b is equal to 0. So this implies b is equal to 0. If I jump down, there you go, that's what it tells me. The other boundary condition, now that I know b is 0, I take this boundary condition and I evaluate it at 1. So for every x, I'd plug a 1 in. There's x, technically there, but b was 0, so it doesn't matter on the cosine term. I'm going to plug 1 in for x, and that's coming from that 1. And so I have a times e to the minus lambda t sine of root lambda equals 0. And you might think the same thing is satisfied here, where I need to let a be equal to 0, because otherwise this would never be 0 for all times. And that's not true. I can actually choose a lambda, so this is true. Well, how do I do that? Well, if sine root lambda were equal to 0, that means root lambda is equal to arcsine of 0, which would be pi. I mean, arcsine of 0 is also 0, but there are lots of values that the arcsine of 0 can take, and in this case, pi is a very useful one. And so lambda equals pi squared is a perfectly valid choice of lambda. And if I scroll down, we're going to see that lambda could actually be, root lambda could be any n pi. And so, and that's because of arcsine, once again, right? So I said arcsine of 0 is root lambda, and I said that this was equal to pi, but in fact, arcsine of 0 is equal to n pi for any n in the integers. This is because of the unit circle, right? Every time I go around a half turn around the unit circle, my y value is still 0, so that's why it's n pi. And if I square both sides, I get that lambda squared is n pi. Okay, so now I know that my solution is equal to, I'm going to replace every lambda with n squared pi squared. Every lambda with n squared pi squared. So I have that this is now my solution. And I have one last step, right? There's a t here. The book's missing. So there's one last step because I haven't used my initial condition yet. Use initial condition. And if I use my initial condition, I'm going to evaluate at time t equals 0. So plugging, remember there was a t there. Plugging 0 in for t, I get e to the 0. E to the 0 is 1. And so I have that a sine n pi x equals sine pi x. And upon finding an a and an n that works for this, the only a comma n which solves this is a equals 1, n equals 1. So now this last condition has given me everything I need. Letting a and n be 1, I recover a unique solution, e to the minus pi squared t sine pi x. And this is an exponentially decaying solution in time, and then in space, it just looks like the sine function, but exponentially decaying over time. And so that's how we go about solving this uniquely. If you look at the plot over time, there's your exponential decay. You start really hot, but since you put ice cubes on the sides, then you exponentially decay to 0. Okay, so that's all I have for today. I know it's a little long, a little tricky. We'll talk more about separation of variables in chapter 15, but now you know how to solve the heat equation. All right, bye.